this. So good morning, and thank you very much to be with us in this the last before the last Athena talks before the summer break, where I would really appreciate your participation. Also, I would like to thank Javier Mateos Ferrer and my colleague Masoud, who has introduced Mateo to this Athena talks. Masoud is not only a colleague but also a very good friend of mine. I have to say this, and I would like to present Mateos. He's going to speak today about structured materials for micro lasers and 2 microns. This is at least, the title. He has modified this a little bit, but it's going to speak about micro lasers. I should be very strict on this about micro lasers. He's a professor in the University of URV University in Tarragona in Spain. Few words about the speaker. He has a very impressive CV and very nice work. Professor Javier Mateos is a full professor at Rovira Virgili University, URV, that's why I mentioned URV, and in Tarragona, Spain. He became recently the group leader of the Physics and Crystallography of Materials Group of Research at URV. Professor Mateos has more than 20 years of experience in material science and laser physics. Solid-state lasers, included thin disk, microchip, and waveguide lasers, and materials, included 2D materials, are his major fields of interest, together with mode-locked ultra-short lasers developed during his postdoctoral stay 2004-2006 at the prestigious and famous Max Born Institute for Nonlinear Optics and Short Pulse Spectroscopy, Berlin, Germany. Another postdoctoral stay from 2015 to 2017 at NBI was as a Marie Skłodowska-Curie Actions Fellow of the EU Commission for the development of a novel 2-micron thin disk lasers. I can see here from your CV, Mateos, we're a small group now, and the Africans, they insist to join this talk, that you have a lot of common things with us. I was a postdoc in Spain, Masoud was postdoc in Spain, you are working with materials, Maria is a professor in material science, you are a Marie Curie Fellow, George Kakavelakis was a Marie Curie Fellow, so I can see that, in this small group, how the people are connected. So I will provide immediately to the floor of his work has received more thousands of citations, and I will give the floor to Javier to guide us to the magic world of micro lasers. And thank you very much. Muchas gracias, Mateos.
Gracias.
Yo hablo español poco, It's the only...
Okay.
Okay, the floor is yours.
Okay. Thank you very much. Thank you very much for this introduction, and thank you very much for this invitation also to give this talk to show you our research activities in our small city. And yeah, congratulations, because I see that this group of researchers, I mean, the atmosphere looks very nice, so it's grateful. Well, if okay, I will share my screen. Yeah. Should be like this. Please tell me if everything is okay, if you can see the screen. Yes. Okay. So yes, I am Javier Mateos from the Physics and Crystallography of Materials Group of Research, which belongs to this small university, Universitat Rovira i Virgili. And today I will talk about structural materials for micro lasers at 2 microns, the spectral range. So just shortly, let me tell you where we are. So we are in Tarragona, the city of Tarragona, which you can see on the map. It's very close to Barcelona. Actually, the science in Tarragona is somehow shielded, by Barcelona, because Barcelona is huge. However, we try every day to contribute somehow from our work to science to some extent, So I can show you also this picture, which is maybe few days old. I mean, it's very new. This picture basically is my research group. which is now composed of 22 people. You can see maybe 2 more experienced researchers here, which are in the process of retirement. So that's why I took over the leading of the research group. And yeah, all these people, who include PhD students, postdocs, and some staff as well, are working basically on lasers and laser materials. This activity is for more than, let's say, 25 years or so. And we recently are also focusing on other topics like nanomaterials, for example, luminescent, dielectric nanocrystals for lighting applications, as well as for sensing, and plasmonics, talking about metallic nanoparticles. So we also started with microfluidics for sensing applications, and we used optics and photonics as a detection in these microfluidic platforms. And recently, we started also working on 2D materials and nonlinear optics with my friend Masoud, who will develop this project in my group. So basically, I will talk then about laser and laser materials, so these microstructure materials. And I have divided this talk in these different sections. So first, I will make a big introduction to know the context we are working with, and later I will give you some examples of some achieved laser results. Okay, maybe here I will give some numbers that you will not or you are not obliged to keep in mind, because probably most of you are not really close to this topic, so many of these things are far, probably. And finally, I will just conclude and talk a little bit about the future work that we plan for the research. So, okay, maybe it's better to read before. So first, in the introduction, I want to talk about a brief overview of our research in general on microlasers, Then I will focus deeper on a special crystal family, which is the monoclinic double tungstate crystals. I will mention like MDT, whose chemical formula is this one. So this is potassium, this is rare earth ions, and this double group of the tungstate. So I will talk about these crystals because we have deep experience, something like 25 years, working on these crystals. And then I will jump to talk about the specific ions which generates the 2 micron laser emission. Currently are the thulium ions and the holmium ions, and I will talk about their main characteristics when we dope these crystals, these MDT crystals, with such ions. And then I will talk about the geometry of the active media. So I will talk about these microlasers under the point of view of 2 concepts. First is the microchip concept, and the second is the waveguide, both at the micro scale. And then I will jump to such examples that I mentioned. Okay, so our research on microlasers, first I want to highlight the microchip concept, which I will explain later. We have been working with, you can see here, different materials. So YAG, for example, YCOP, or the well-known and famous family of these fluorides crystals, as well the Sesqui oxides. Yeah. So all of them doped with ytterbium for lasers at 1 micron, or thulium for lasers at 2 microns, and many others ions like holmium, which operates at 2.1 micron, or erbium at 1.5 microns, so, or 1.6 microns. So in general, the message here is that we that we have been working on microchip lasers with several laser materials. I just put here some examples, as well as some spectral ranges. So I mentioned here 1 micron or 1.5 micron, 2 microns, etc. So this concerns the microchip lasers. As for the waveguide lasers, which is the other concept for micro lasers, we also explored many materials. So as example, this aluminate, this calgo, or this monotungsten, magnesium monotungstate, or calcium fluoride, for example, and explored something similar than in the previous case, different active ions to target the different spectral ranges, basically in the infrared, so 1, 1.6, and 2 microns. Okay. Well, besides these different kind of materials, I will focus more today on the monoclinic double tungstate crystals. This family of materials, you can see here the chemical formula. It is potassium, rare earth. Rare earth typically includes yttrium, gadolinium, or lutetium, which are passive ions in the structure. And they are doped with these lanthanide ions, which are the active ions that substitute for the passive ions. And among the active ions, we find, so for example, ytterbium for 1 micron, thulium for 2 microns, erbium, blah, blah. And today I will focus on 2 micron lasers. So I will talk more about thulium and holmium ions. Basically, these crystals, okay, they have some advantages and some disadvantages, I would say. In general, I will tell you that these crystals, for optical understanding, first we need to consider that they are monoclinic crystals. So they are biaxial, and they belong to the space group C2 bar C with the point group 2 bar M. The main characteristic is that they accept high doping levels of the active ion, which is very interesting for some applications. They accept then high doping levels. Indeed, you can dope with typically few percent, atomic percent of substituted passive ion, but you can scale at 10, 20, etc. Even we have demonstrated 100% substitution, which means that you have an active ion, which is a structural ion, like, for example, ytterbium or erbium. Well, as for the thermal conductivity of this material, this is somehow a drawback because it is moderate. So the application for lasers is mainly for low to medium powers. And once we dope these materials with the lanthanide ions, with the active ions, so the good thing is that they show very large transition cross-sections, which is very, very interesting. And, they also show broad absorption and emission bands, which also is interesting, for example, for the generation of ultra-short laser pulses, which we have also demonstrated, but I will not talk about this today. And the good thing is that they show weak concentration quenching because, as I mentioned before, they can be heavily doped, and because the ion-to-ion distance, the rare earth and rare earth distance inside the structure is quite long, and the interaction is not really is really so that there is no significant concentration quenching of the luminescence of this ion. Besides these characteristics, they also show strong Raman activity, also with commercial application as Raman shifters. So we have published this interesting paper, which gathers, is a kind of review, which gathers many of these properties of this family of crystals. So if someone is interested, you can have a look to this paper. I'm very proud of this manuscript. That's why I'm mentioned like this. Yeah. So now focusing on these specific crystals, these monoclinic double tungstate lasers, and with the geometry of microchip, we have contributed in several spectral ranges, like 1 micron, for example, with ytterbium, also at 1.6 micron with erbium. So note that I'm again summarizing something similar than before, but now only focusing on the monoclinic double tungstate crystals. And as you can see, the production with these materials is quite high, because you can always substitute the ion, the active ion, and also use the passive ion, and you will always find some differences and new characteristics. So we have studied not only continuous wave lasing, but also pulsed lasing by this technique, the Q-switch, the passive Q-switch technique, and as well as at several wavelengths. Yes, for example, this 1 micron, 2 microns. Well, as example, I put this MOS2 two-dimensional material as saturable absorber for passive Q switching, but we have explored several of them. The saturable absorber, okay, I assume you know this. This is a passive element in the cavity that allows for pulse generation. So besides these microchip lasers with this family of crystals, we also went to the waveguide geometry with the same crystals. And basically here the waveguide has been fabricated by means of femtosecond laser writing. So with this technique, with the help of a collaboration also of a Spanish group, we have fabricated a lot of waveguides, and then explored the laser capability of several ions, like again erbium, for example, here, or ytterbium, also thulium, and holmium, in both in continuous wave and pulse regime. Pulse regime, again, with this technique, Q switching technique, as well as sub picosecond pulses by the mode locking technique. So, having seen this as a general overview of the activity on microlasers, so we can talk then about microlasers with different family of materials, and more specific with these MDT crystals. And now I'll talk about the ions for 2 micron lasers, more specifically thulium and holmium. Well, just as examples, I show you here some thulium dope crystals, MDT crystals, in this case with lutetium, which are grown in my laboratory, and we orient these monoclinic crystals according to you can see here in this drawing, as a green, the crystallographic axis, and in red, the so-called principal optical axis. Yeah. So we cut these crystals according to these orientations, and we polish them for laser quality. You can see here these 2 examples. Okay, maybe later I will come back to this figure, because these orientations, as we will see later in the spectroscopic properties, depend on the polarization of light, which is parallel to exactly these principal optical directions. Then I will need to come back to this figure. So as for the spectroscopy, which is to understand the laser operation and laser capabilities and laser potential of these crystals, I show you here some, maybe the most prominent information, without trying to go too much into detail. Just here I show you the absorption properties of thulium. Absorption properties of thulium, depending on the on how the polarization of the incoming light is reaching the crystal according to the three principal optical directions that I mentioned before. So you can see, for example, that when light is parallel to the so-called NG principal optical direction, which is associated to the biggest refractive index in the crystal, the absorption is almost nothing, so it is insignificant. However, for the other two principal optical directions, the absorption is very anisotropic and very large. So here we can strategically decide what is the best pumping characteristics. For example, if we are going to use laser diodes for pumping, you can explode the broadband absorption for this principal optical direction, because then the bandwidth of the requirement for the laser diodes is not so strict. So this is actually what we are doing, pumping at this absorption band. This concerns the absorption, and if we go to okay, this is the around 800 nanometers in the spectral range. If we go close to the 2 micron, where we expect to get the laser emission, you can see for the case of thulium in black, you see the absorption characteristics, and in blue, you see the emission characteristics. So we calculated from these emission and absorption curves, the so-called gain cross-section of the material. So how much the material is potential how much is the potential to provide laser operation in this region where you have net emission, so expected net gain, yes. And we have calculated this for these two principal optical directions, because as I mentioned, the red one, so-called NG, is in principle not very interesting. So one can expect that we will use this direction as a propagation direction in the crystal to have access to these two polarizations of light. Yeah. Okay, this concerns thulium, which seems typical quasi-3 level laser. So you pump around 800 nanometers, and then you expect a laser operation around 2 microns. Yeah, maybe slightly shorter than 2 microns. The case of holmium is a different story, because holmium has an absorption band in black again, which also is around 2 microns, and you can see an emission band which has positive gain slightly above 2 microns at the end of the tail, let's say, of the absorption band. So we expect laser operation here, while we can explode the emission from thulium around 1.9 microns to excite the holmium ions, and then to achieve laser operation well above 2 microns. And why is this important? Is because maybe you know that water absorption or water vapor absorption is quite prominent in this region, around 1.9 microns, just below 2 microns, while in the case of holmium, we then avoid this water absorption. Well, these are the spectroscopic properties, or maybe the most important spectroscopic properties of these two ions. So we're talking about microlasers, the microchip concept, we're talking about the waveguide concept, but what is this? So for those who are not familiar with the microchip concept, I will just make some hints so that you understand the most relevant information. So microchip concept is as easy as a sandwich-like laser resonator. So we use the active material, the laser crystal, which is in blue here, between two plane mirrors. These two plane mirrors can be physically plane mirrors, or you can directly coat the crystal so that you gain in compactness and you gain in insensitivity to misalignment as well. So the cavity length is just imposed by the length of the crystal. So we are talking here about micro lasers, which means that we are talking about crystal lengths of few hundreds of micrometers, which means that you need huge gain per unit length to have and absorption, to have good absorption per unit length, and then high gain per unit length to have good efficiency and good output in terms of power. So that's why here the MDT crystals have some advantage, because I mentioned before that you can heavily dope them. You can dope 3% atomic percent, 10 atomic percent, you can go up to 25 atomic percent and even more. So this means that the absorption length is reduced, and you have very good absorption in a very short crystal length. So it is very suitable for this laser concept of the microchip. And this microchip concept gives you very high degree of compactness and robustness, and they give high efficiencies, because you can understand that you have absence or reduced losses because of these air gaps between the mirrors and the sample, and it is even better if you directly coat the crystal. Yes. However, as you probably know, a plane resonator needs kind of mode stabilization, because it is not, the mode stabilization is not stable. So you need an additional term to stabilize the laser mode inside this cavity, which is provided by the so-called thermal lens, which should be positive. So if the thermal lens in the crystal is positive, then the laser mode will be stable inside this plane resonator. And this is given, okay, I don't want to go too much into detail. If someone wants to ask me about this, I can answer many things, but just few comments. The thermal lens is given by these three thermo-optical coefficients, basically the variation of the refractive index with temperature. This is due to the photoelastic effect, so how the refractive index changes with the thermally induced strain stress in the crystal, and this term is due to the thermal expansion of the crystal. So the sign of this term, if you add all of them, the sign will provide you the key to stabilize this laser mode in the cavity. Well, in the case of the MDTs and of the monoclinic double tungstates, this term, the first term is negative, the second term is negligible, and the third term is positive. In a sense, the sum of all of them gives you a weak but positive thermal lens. This is the optical power of the thermal lens. And then they have positive thermal lens for one of the three principal optical directions, the one which is called NG, I mentioned before, which showed very poor absorption properties, but it shows positive thermal lens, meaning that the combination is somehow perfect. Yeah. So light will be propagating along this direction, which shows positive thermal lens, while we will have access with the polarizations to the other directions with higher absorption and emission cross sections. So it looks like the combination is perfect. And another advantage of this concept, the microchip concept, is that you can insert a passive element so-called saturable absorber, a passive element here which provides you the capacity to generate laser pulses. Like I mentioned here, we used, for example, graphene or this molybdenum disulfide that we have seen before to generate these laser pulses through the Q-switching technique. Well, this concerns the microchip concept, and now I jump to the waveguide concept. I don't know to what extent you are familiar with this, but basically what we tried is to confine light in a very small region in the crystal. So you can see this drawing is very clear because it shows the refractive index of the material, of the bulk material. And at some moment, with the femtosecond laser writing, we amorphize locally the crystal so that the refractive index drops to some extent, and inside the structure it is preserved constant. And again, at this other part of the we'll call cladding, the refractive index again drops. So this means that what we have in a sense is that we have created with the femtosecond laser, we have created a region where the refractive index is lower than the refractive index of the core, so that the light will be confined within this region. So for this, we have a strong collaboration with another university in Spain, and they use this laser to produce the local and controlled damage of the so-called cladding. And we have designed several geometries, like for example this one, which is, you can see here, air, and then we have the crystal, so that we have fabricated a buried waveguide, maybe something like 150 microns deep from the surface, and we put attention to the crystal orientation, as you can see here. So light will propagate along this, again, NG principal optical direction. We also have designed several shapes of the cladding to improve the confinement, sometimes also confining or making stronger the confinement along one direction only. And as you can see at the bottom, we also have this designed the so-called not buried but surface waveguides. So we have damaged locally the crystal on top of the, let's say, in contact of the surface, so that light will propagate inside of this waveguide, and the evanescent field of the propagating laser will interact with whatever we deposit on top of this waveguide on the surface. And we also applied several other geometries like this one. This is the exit of a waveguide, which is actually a beam splitter. That's why there are two arms, one of the beam splitter. Well, for these waveguides, we did some characterizations like confocal microscopy to study how the laser affects the structure. This is an end view, and this is the top view of the waveguide. Basically, here we can observe this damage under the so-called cross-polarizer characterization, because, as you know, with cross-polarizers, the transmission of light should be 0, but due to this local damage of the crystal, what we are doing is basically locally we vary the optical indicatrix. So what we vary is the angle of these principal optical directions, and then part of the light is transmitted. That's why we can see some bright areas. Well, further characterization of the waveguides, this is an example of a surface waveguide, is to study how the crystalline structure is let's say amorphized, or how is it changing with the laser. And for this we have measured a Raman mapping. Raman mapping basically means that we study first the Raman characteristics, Raman spectroscopy of our crystal. And for example, if we focus on one of these stretching vibrations, which in this case is the most intense one, around 900 wave numbers, so we can monitor the peak intensity, and we can monitor the peak frequency or the peak width all along the sample, all along the damaged area. And then we can notice, for example, in the case of intensity, you can see the parts of the core and outside the cladding in red, how the intensity is in arbitrary units here, and then how it drops in the parts where the laser has damaged the crystal. Okay, and the same for the peak frequency or the peak width. For example, this is another one. This was the surface channel waveguide. This was a buried channel waveguide. And here, instead of monitoring this Raman peak, we have monitored another one, which is related to this double oxygen bridge stretching vibration. And we have monitored exactly the same peak intensity, peak position, and peak width to observe somehow the quality of the damage, how the core is preserved, and how is the collateral stress induced by the femtosecond laser in the structure, I mean in the crystal around the waveguide. So more or less, I have overviewed these two concepts that we have been using. I mean, the microchip and the waveguide concepts. I have been talking about the monoclinic double tungstate crystals. I have talked also about these two specific ions for 2 micron lasers. And now I will just give some examples of results that we have achieved. Maybe here, as I mentioned before, there are some numbers that maybe are unimportant if you are not in the field, but I want to show you because some of them are quite relevant, I mean, in the field. I will talk about continuous wave and passively switched thulium and or holmium microchip MDT lasers, and the same with the waveguide concept. Okay, so let me start with the crystals that we have studied. This again are some examples of single dope thulium MDT crystals, holmium, or for example, this is holmium KGW. So here we changed the passive ion, or even we went further to co-dope the crystal with thulium and holmium. These crystals, we use the top-seeded solution growth method to grow them. And typically we use several doping levels, but only few atomic % substitution of the passive ion. Yeah, typically these are the doping levels, only with the exception of even more heavily doped crystals if we want to reduce further and further the length of the active medium. And typically we use, as I mentioned before, the so-called NG direction as a propagation direction, and then to have access to the positive thermal lens and to give access to the two polarizations with higher cross-section, NM and NG. So, okay, let's start with the microchip laser results. This is the typical laser setup that we implement for the thulium 2 micron lasers. This is a commercial laser, and then we re-image the output of the laser, of the diode laser, into this very compact cavity. So here you can see the pump mirror and the output coupler. So for output coupler, we use typically several transmissions of this output coupler, and then to know how the laser behaves according to the different losses that we are implementing in the cavity. And in the case of holmium, as a pump source, we use our previous thulium laser. So this is the thulium laser here that you have here, and this thulium laser, which is homemade, we use to excite the holmium laser, to study the holmium lasers. Well, if we start with the thulium MDT microchip lasers, you can see here that we typically study the output input characteristics, so the output power against the absorbed power. Okay, maybe I don't need to explain all these numbers, but you can see that here we also studied this output power against the absorbed power as a function of the output coupler. Also, we did some modeling to have better overlap between the pump and the laser modes in this cavity. For example, we have used typically pump mode of 100 microns, while the calculations gave us a result of about 50 microns for higher absorbed power. So if we want to scale in power, what we need to do is just to reduce the pump spot, just either by reimaging or by using a fiber with smaller core. But typically our intention is not going for higher power, just to demonstrate the concepts and to demonstrate that these crystals are working. So, for example, just as a matter of fact, we have also calculated what will be the stability of the cavity according to the absorbed power, depending on the mode matching. So actually, we could have huge absorbed power, something like 40 watts. Imagine that here we have only 6-7 watts of absorbed power, while here we can go with proper mode matching, we can go up to 40. So if you consider this low efficiency, this will mean an important power scaling of these lasers, which is in principle not our intention. So also we have studied pulsed operation using, in this example, two saturable absorbers, so the MOS2 or graphene, where basically, okay, beyond the numbers, just I want to highlight the high conversion efficiency, for example, of the MOS2, up to 81%. Conversion efficiency means with respect to the continuous wave mode. Okay, basically these saturable absorbers are from some collaborators. So we have them from other collaborators. Some of them have good quality, others have worse quality. So we are always fighting with such things. I can imagine you as well. And we characterize so the laser spectra of these lasers and many other characteristics like the pulse duration, for example, as a function of the absorbed power, or the pulse energy as a function of the absorbed power. You can see here some numbers, something like pulse durations below 200 nanoseconds, or pulse energies of about 6 to 8 microjoules. And further characterization is about the temporal profile of the shortest nanopulses, nanosecond pulses, and the stability of the pulse train, which in this case is not really very stable. And we attribute this typically to the fact that, imagine you have the microchip laser, so you have a crystal, and behind the crystal you have the saturable absorber. So most of the power which is not absorbed, the pump power which is not absorbed, will reach the saturable absorber, and then depending on its nature, it will be affected. The stability will be affected just by heating or whatever. So with this concept, we could publish several results. These are focused on 2 microns essentially. So for example, this one, which is in CW, the other one, which is pulsed operation with graphene as a saturable absorber, all of them with thulium and this MDT crystal. Also, we have used more standard saturable absorbers like this chromium zinc sulfide, providing sub-nanosecond pulses in this very short cavity, or the MOS2, which was applied not only for 2 microns, but also for 1 micron microchip lasers. So if we move from thulium to holmium, which is the second ion that provides 2 micron emission, as I mentioned, we use the thulium microchip laser to pump the holmium microchip laser. And we have done quite deep study of these lasers also, not only studying the output input characteristics like this one, achieving very high slope efficiencies approaching 90%, which is the quantum limit. But also we have explored, for example, different focal lengths of the focusing lens. You can see here the theoretical study as well as the experimental study, to have or to achieve the best mode matching of the pump and laser modes in this resonator. And then with the best one, we can then achieve the best performance as possible. Like in this case, more characteristics are, or more work has been devoted to the correlation between the laser wavelength, depending on you can see here, the different transmission of the output coupler, meaning that the wavelength depends on the losses that you apply in the cavity. The higher the losses, in principle, the shorter the wavelength, which oscillates. And this is because this material, well, these ions the nature is quasi 3-level laser. So there is some reabsorption from the ground state, and according to the calculated gain curves, these are the calculated gain curves. So these are from the emission and absorption curves, so that we can estimate and then we can correlate the laser wavelength according to the inversion population beta in the material. For example, if we have high losses, the material needs to create high inversion. Let's say, for example, these values, high inversion, so that the maxima, the local maxima of the gain curves are moving, if you follow, from low inversion levels to high inversion levels, it shifts to longer wavelengths. And this is what we observed, not only in this material, but also in terbium, thulium, and also here holmium. So that we can determine that how much is the inversion according to the laser wavelength. So for these holmium lasers, we did similar characterization than compared to the thulium. So for the passive operation, where we insert again the saturable absorber behind the crystal, we observed or we studied how the pulse duration behaves with the absorbed power and all these characteristics of output power, the pulse train stability, the conversion efficiency, and all these characteristics which are typical in the characterization of these lasers. And as a result, we also published intensively on this ion, on this holmium ion. For example, this is for CW with very high slope efficiency, and also here the pulsed operation. In this case, the saturable absorber were this PBS, so lead sulfide quantum dots. Well, besides the thulium microchip lasers and the holmium microchip lasers, we also combined the two ions because it is well known that if you excite the thulium ions with this cheap and commercial diode lasers, because the existence of resonant energy levels, they can transfer the energy from the excited ion to the holmium ion, and then to achieve lasing from the holmium ion above the 2 micron. And this is what we did in this experiment. So we again studied systematically all the characteristics of the laser. Again, we can correlate the laser wavelength with the gain curves of holmium, and not only because of the transmission of the output coupler, not only with the losses that we apply in the cavity, but also with the different level of absorbed power, which is related actually to the temperature, of the crystal, modifying the inversion level, then modifying the gain shape, and then shifting the wavelengths to shorter wavelengths when increasing the absorbed power. Well, we have done many characterizations. So again, about the laser performance, the pulse durations, the stability of the pulse train, the beam profile. So all these characterizations are typical in these studies. And as a result, again, with this co-doped material, we have good production in terms of publications. Well, in the post or CW regimes, and with one saturable absorber more standard, with another saturable absorber maybe more novel. And as a result, we have published a few years ago this review, which is gathering all the information about the micro lasers in the microchip, with the microchip concept, for the MDT crystals, for the crystals that we have grown in our lab. Okay, so this concerns the microchip concept. Then I will move to some results based on the waveguide concept. But you can see that the arrangement is rather similar. So we have a plane mirror, and then we sandwich the waveguide between them. Alternatively, if we want to study Q switching, then we insert the saturable absorber. This is typical arrangement for buried waveguides. And instead of using laser diodes, we have done this characterization of this waveguide lasers using a Ti-Sapphire laser tuned to the maximum of absorption of these crystals. And very similarly for the holmium waveguides, in this case, by using the same thulium MDT microchip laser as a pump source. So, well, again, a lot of information here. We have successfully achieved continuous wave lasing in the buried thulium waveguides. And again, we studied the output characteristics. I have to say that we achieve watt level from these waveguides, which is very high output power indeed for this kind of lasers. We also determined the slope efficiencies for many output couplers, and also we estimated the propagation losses for several waveguide geometries like 50 microns in diameter, 60 microns in diameters, etc. So here you have some numbers. And we went further with the characterization of pulsed regime, so not only in the CW, in the continuous wave, but also the pulsed characteristics of the lasers achieved with graphene, a saturable absorber of this MOS2. Look that I'm constantly repeating these two saturable absorbers just for comparison, but we have studied many other saturable absorbers. And again, we always try to correlate and to give evidence of these results by relating or correlating the laser wavelength with the gain curves and things like this. And these again are the characteristics of these lasers. So the pulse duration, pulse energy of these waveguide lasers. And again, there is a constant which is negative in these lasers, I would say, and it is about the intensity instabilities, because the pulse trains are not really constant, not really stable, because again, this heating of the saturable absorber due to the non-absorbed power from the crystal. Well, again, this is what I mentioned about the stability of the pulse train for the two saturable absorbers. So this is a constant, and that's why we moved to a different geometry. So the strategy here was to avoid this residual pump heating the saturable absorber by depositing the saturable absorber on top of the waveguide. This is then the so-called surface waveguide, and then that's why we went to fabricate the waveguides with this shape on top of the crystal, just because then we could deposit the saturable absorber on this surface and to avoid these instabilities. With this new geometry, we studied the laser. We started with thulium. Again, we repeated the experiments. We achieved these nice results. Again, we did all the characterization of propagation losses and all the systematic work to be sure that everything was under control and everything was deserved to be studied. And maybe the most important result here is that we increased the conversion efficiency from continuous wave to passively switched operation to almost 90%. And the second more important information is about the instability of the pulse train, which was clearly much better than before. So maybe the instabilities were in the range of 20%.
Actually, you should somehow complete the talk within the next 5 minutes.
Yeah. Okay. I'm sorry. Maybe I'm giving too many information. So basically, this is the advantage of working with the surface waveguides. Okay. And then we also applied them to holmium buried, and then to holmium surface waveguides. Okay, again, I can show you these results just quickly, and if you have any question, we can discuss more. And finally, as a result, then with this geometry of waveguide lasers, we could publish also very nice works with thulium, with holmium, in continuous wave regime, also in the pulsed regime, with several saturable absorbers, as you can see here in these papers. So quickly to conclude, just I wanted to show you the framework of our work in microlasers, talking about this microchip concept, the waveguide concept, and focusing on these monoclinic double tungstate crystals. But besides these crystals, we have explored many others, as I mentioned in the beginning. We studied different temporal regimes. We studied, as you can see here, different saturable absorbers. And well, maybe just to thank especially our funding, because without funding, it would be impossible to work in this way. And of course, thank you for your attention. I'm very sorry for the time. Maybe it's
No. Don't
1
worry.
hour.
Other
1
people,
hour.
probably, they have other meetings and stuff like this, but it was a very
Yes.
nice talk. I
Yes.
can see, from the reaction of the people, like from George Pavulakis, when it takes very interesting results. Unfortunately, I have to leave since I have another meeting, but it was like something very, very unique, very innovative as a construction. If there are, we have time just for 1-2 questions. Please, Javier, please stop sharing the screen in order, to check
Yes.
for the people that they have stayed. Their questions.
Just one.
I have one a question like how can we tune the output wavelength of these devices, Javier? Like it's like classically by tuning the temperature, by tuning the pump source. What is the maximum tuning, wavelength tuning can be achieved with these devices?
Okay.
Continue
Yes. Thank you
tuning.
for sorry. How can I? Here.
Yeah.
Okay. Now it's better.
So
Now it's not shared.
what is the largest continuous tuning that you can do, or with mod hop tuning? What is like, these capabilities?
Yeah, typically, these materials, because they have broad emission band, they can be tuned. And we explore the tunability of these lasers by using a long cavity. Then with a long cavity, you can insert the proper elements like a LEO filter, for example, and then you can systematically include different losses to tune the laser. But in these short cavities, the laser wavelength is fixed by the losses given fundamentally from the output coupler. So just by changing the transmission of the output coupler, then the wavelength will shift according to the gain curve, and this is the way you can somehow.
This is not so convenient to change the output coupler, eh? No?
Sorry?
It's not so convenient to change the output coupler, no?
Yeah, absolutely. If you want, for example, to work for higher output power and you fix the output coupler transmission, then you have a fixed wavelength.
Yes.
This is true.
Yeah. And then what is the reason why you see, okay, micron laser, okay, so this is like another question that I would like to do, but it's not valid because I'm going to ask you why you don't go to a longer cavities in order the free spectral range to be closer, in order, to have more tuning, but this is not possible since we're talking about micro.
Exactly.
But micro lasers, okay, so it's not, yeah, okay, never mind. I got the answer. And you mentioned about the application of the thermal lens in order to control the mode. I suspect that you are talking about the transversal mode of the laser, no?
Transversal mode. Yeah.
Okay.
Transversal
Okay.
mode.
And the output is like strongly polarized, or is like, what's the polarization?
Absolutely. It is strongly polarized because, as you have seen, these materials are anisotropic, and the gain is very different from one another polarization. So the polarization is naturally selected by the gain, which is typically much stronger for this optical direction, principal optical direction, which is called NM. Yeah.
Yes. CW operation can be achieved with this kind of devices.
Sorry?
CW operation can be achieved with these devices. Continuously.
Yes. I have shown continuous wave operation has
Without the
been
structural absorber, I suspect, no? Without the structural absorber.
Exactly. Without the saturable absorber, we achieve continuous wave operation. And once you insert the saturable absorber, you achieve the nanosecond pulses.
Thank you. It was very nice.
Okay,
but of course, from the nano lasers, I can see that, in some cases of nano lasers, you don't need population inversion, for example. In this case,
it's a different story.
Do you need population inversion? They operate, as usual.
As usual, yeah.
Okay. All right. Thank you so much.
Okay.
I have realized that the 2D materials, the role of the 2D materials is mainly as a structural absorber, no?
Correct.
Yeah.
Correct.
Excellent. From my side, I don't have any other questions or reconfirmations. So I suspect that people also they were joined, but after 12 o'clock, I think that they have other plans. So are there any questions from the remaining audience here about the talk, about the speaker? Okay, so I cannot see any question. Javier, I would like to thank you. It was a very nice talk.
Thank you.
And I'm going to send you an email about, and also Masoud, I place also a note about Masoud to join this photonics hub that we are trying to create in order to organize more coherent and more events in this topic. So I would like to thank you very much.
Thank you. Thank you. And
Okay, Kostas, thank you very much also.
Bye. Bye. Bye.
Bye. Thank you.